In this presentation, I'll go through some notes from Chapter 3 of the book, Designing Data-Intensive Applications. Chapter 3 is called Storage and Retrieval. Here is a nice image from Chapter 3. As you can see, we'll be diving into ocean of distributed data and sea of storage and retrieval. So I'll go through the highlights first. So this chapter tried to get to the bottom of how databases handle storage and retrieval. What happens when you store data in a database, and what does the database do when you query for the data again later? On a high level, we saw that the storage engines fall into two broad categories, and those optimized for transaction processing, also called OLTP, and those optimized for analytics, also called OLAP. OLTP systems are typically user-facing, which means that they may see a huge volume of requests. In order to handle the load, applications usually only touch a small number of records in each query. The application requests records using some kind of key, and the storage engine uses an index to find the data for the requested key. Disk seek time is often the bottleneck here, if this is a disk-oriented database. Then the data warehouses and similar analytics systems are less well known because they are primarily used by business analysts, not by end users, and this is changing. They handle a much lower volume of queries than OLTP systems, but each query is typically very demanding, requiring many millions of records to be scanned in a short time. Disk bandwidth, not seek time, is often the bottleneck here. And column-oriented storage is an increasingly popular solution for this kind of workload. On the OLTP side, we saw storage engines from two main schools of thought. The first is the log-structured school, which only permits appending to files and deleting obsolete files, but never updates a file that has been written. Bitsask, SS tables, LSM trees, LevelDB, Cassandra, HBase, Lucene, and others belong to this group. The update in place school, which treats the disk as a set of fixed-size pages that can be overwritten. B-trees are the biggest example of this philosophy, being used in all major relational databases and also many non-relational ones. Log-structured storage engines are a comparatively recent development. The key idea is that they systematically turn random access writes into sequential writes on disk, which enables higher write throughput due to the performance characteristics of hard drives and SSDs. So that covers the highlight. Now let's look at some notes. So first is index. An index is an additional structure that is derived from the primary data. Many databases allow you to add and remove indexes. And this doesn't affect the contents of the database. It only affects the performance of queries. Maintaining additional structures incurs overhead, especially on writes. Any kind of index usually slows down writes because the index also needs to be updated every time data is written. This is an important trade-off in storage system. Well-chosen indexes speed up read queries, but every index slows down the writes. For this reason, database doesn't usually index everything by default, but require you, the application developer or database administrator, to choose indexes manually using your knowledge of the application's typical query patterns. Hash table index limitations. The hash table must fit in the memory. So if you have a very large number of keys, you are out of luck. In principle, you could maintain a hash map on disk, but unfortunately, it is difficult to make an on-disk hash map perform well. It requires a lot of random access I/O. It is expensive to grow when it becomes full, and hash collisions require fiddly logic. Range queries are also not efficient. For example, you cannot easily scan over all keys between kitty 00000 and kitty 99999. You'd have to look up every key individually in the hash maps. B-tree optimizations. There are quite a few listed in the book, so I'll go through them here. Instead of overwriting pages and maintaining a write-ahead log for crash recovery, some databases like LMDB uses a copy on write scheme. A modified page is written to a different location, and a new version of the parent pages in the tree is created, pointing at the new location. We can save space in pages by not sharing the entire key, but abbreviating it, especially in pages on the interior of the tree. Keys only need to provide enough information to act as boundaries between key ranges. Packing more keys into a page allows the keys to have a higher branching factor, thus fewer levels, which is the idea behind B+ trees. In general, pages can be positioned anywhere on the disk. There is nothing requiring pages with nearby key ranges to be nearby on disk. If a query needs to scan over a large part of key range in sorted order, that page-by-page layout can be inefficient because a disk seek may be required for every page that is read. Many B-tree implementations therefore try to lay out the tree so that the leaf pages appear in sequential order on the disk. Additional pointers have been added to the tree. For example, each leaf page may have references to its sibling pages to the left and to the right, which allows scanning keys in order without jumping back to parent pages. B-tree variants such as fractal trees borrow some log structure ideas to reduce disk Cs, and they have nothing to do with fractals. B-trees versus LSM trees. Even though B-tree implementations are generally more mature than LSM tree implementations, LSM trees are also interesting due to their performance characteristics. As a rule of thumb, LSM trees are typically faster for writes, whereas B-trees are thought to be faster for reads. Reads are typically slower on LSM trees because they have to check several different data structures and assess tables at different stages of compaction. Here are some of the advantages of LSM trees. A B-tree index must write every piece of data at least twice, once to the write-ahead log and once to the page tree itself, and perhaps again as the pages are split. There's also overhead from having to write an entire page at a time, even if a few bytes in that page have changed. Some storage engines even overwrite the same page twice in order to avoid ending up with a partially updated page in the event of a power failure. Log structure indexes also rewrite data multiple times due to repeated compaction and merging of SS tables. This effect one write to the database resulting in multiple writes to the disk over the course of database lifetime. This is also known as write amplification. It is of particular concern on SSDs, which can only overwrite blocks a limited number of times before wearing out. In write-heavy applications, the performance bottleneck might be the rate at which the database can write to disk. In this case, write amplification has a direct performance cost. The more data storage engine writes to disk, the fewer writes per second it can handle with the available disk bandwidth. Now let's look at some of the downsides of LSM trees. A downside of log structured storage is that the compaction process can sometimes interfere with the performance of ongoing reads and writes. Even though storage engines try to perform compaction incrementally and without affecting concurrent accesses, disks have limited resources. So it can easily happen that a request needs to wait while the disk finishes an expensive compaction operation. The impact on throughput and average response time is usually small, but at higher percentiles, the response time of queries to log structured storage engines can sometimes be quite high, and B-trees can be more predictable. An advantage of B-trees is that the key exists in exactly one place in the index, where a log structured engine may have multiple copies of the same key in different segments. This aspect makes B-trees attractive in databases that want to offer strong transactional semantics. In many relational databases, transaction isolation is implemented using logs on ranges of keys, and in a B-tree index, those logs can be directly attached to the tree. Clustered index. In some situations, the extra hop from the index to the heap file is too much of a performance penalty for reads, so it can be desirable to store the indexed row directly in an index. This is known as a clustered index. For example, MySQL's InnoDB storage engine, the primary key of a table is always a clustered index, and second indexes refer to the primary key rather than a heap file location. A compromise between a clustered index that is storing all row data within the index and a non-clustered index that is storing only references to the data within the index is known as covering index or indexed with included columns, which stores some of the table columns within the index. Column-oriented storage. The idea behind column-oriented storage is simple. Don't store all values from one row together, but store all the values from each column together instead. If each column is stored in a separate file, a query only needs to read and parse those columns that are used in that query, which can save a lot of work. Besides only loading those columns from disk that are required for a query, we can further reduce the demands on disk throughput by compressing data. Fortunately, column-oriented storage often lends itself very well to compression. Now, this table captures the OLTP versus OLAP characteristics, as we can see. Let's look at the properties one by one. Main read pattern. In the OLTP system, there's a small number of records per query fetched by key. In OLAP, there's an aggregate. Typically, the read patterns are, we aggregate over a large number of records. The second property is the write pattern. In OLTP, there's generally it's random access, low latency writes from user input. In OLAP, generally the write patterns include bulk import, that is ETL or event stream. The third property is primarily used by OLTP systems are typically used by end user or customer via web applications. OLAP systems are generally used by internal analysts for decision support. The other property we can look at is what data represents. In OLTP system, the data is typically the latest state of data, that is current point in time. In OLAP is the history of events that happened over the time. Data size. In terms of data size, the OLTPs are in the order of gigabytes to terabytes, depending on, again, the businesses, and then OLAP, it can go from like terabytes to petabytes. It's just because we are storing a lot of history. Now, star versus snowflake schema. Here there is a typo. Instead of start, it should be a star. The name star schema comes from the fact that when the table relationships are visualized, the fact table is in the middle, surrounded by dimensions table. The connections to these tables are like the rays of a star. A variation of this template is also known as snowflake schema, where dimensions are further broken down into subdimensions. So it gives you a snowflake like mental model. Materialized views. Another aspect of data warehouses that is worth mentioning briefly is materialized aggregates. As discussed earlier, data warehouses queries often involve aggregate functions such as count, sum, average, min, max, median. If the same aggregates are used by many different queries, it can be wasteful to crunch through the raw data every time. Why not? So the question is, why not cache some of the counts or some that queries most often make? One way of creating such a cache is materialized view. In relation data model, it is often defined like a standard virtual view, a table-like object whose contents are the results of some query. The difference is that a materialized view is an actual copy of the query results written to disk, whereas a virtual view is just a shortcut to writing queries. When you read from a virtual view, the SQL engine expands it into the view's underlying query on the fly and then processes the expanded query. When the underlying data changes, a materialized view needs to be updated because it is denormalized copy of the data. The database can do that automatically, but such updates makes write more expensive, which is why materialized view are not often used in OLTP databases. In read-heavy data warehouses, they can make much more sense. Whether or not they actually improve read performance depends on the individual cases. Cool. So this concludes Chapter 3 notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.